Welcome! In this unit, you'll be learning about exponential and logarithmic functions. You've already spent a great deal of time learning about functions, but these two functions are so special that they're worth their own unit. These functions get used a lot in applications, so let's start with an application to see why we need an exponential function and a logarithmic functions, and why the ones you've learned so far won't suffice. Let's begin by looking at an example to understand why we need the exponential and logarithmic functions. Suppose we have a bunny. And if this bunny has a bunny every month, well, after 1 month, we'd have one bunny. After 2 months, he would have a bunny, and we would have 2 bunnies. After 3 months, each of those 2 bunnies would have a bunny, and we'd have 4 bunnies. If each of those 4 bunnies had a bunny, we would have 8 bunnies, and so on. And eventually, we'd have a ton of bunnies. So suppose we track the bunnies' population over time. What if we wanted to know how many bunnies there were after a month, after 2 months, after 5 months, after a year, after 5 years, after a century? To do these sorts of calculations, we would need to have some sort of function which captured the doubling behavior of the bunny population. So the function we're going to look at is something called the exponential function. We see we have a graph, and in this graph we see the population of the bunnies for several iterations. We started with 1 bunny, then we had 2, then we had 4, and so on. What kind of function matches this behavior? Well, if you look back at think about the catalog of functions you already know. You know linear functions, polynomial functions, rational functions, and you try to think about this curve over here. Well, what does that look like? This curve doesn't look like any of the curves you're familiar with. You might guess a parabola because it seems to be curving up. However, that won't work for this population. If we want to match this with a curve, it would have to look something like this. And that curve is getting steeper and steeper because this population of bunnies is getting large very, very quickly. And that brings us to the need for the exponential function. In John Napier's book, A Wonderful Description of Logarithms, he described how the logarithm was such a useful tool to help do calculations for celestial mechanics. This book was the first one of its time to describe how a logarithm could be used to turn hard multiplications into simple additions. He also gave a table of logarithmic values, which was used for hundreds of years afterwards. Another mathematician, Leonhard Euler, played a large role in the development of the exponential and logarithm functions. Leonhard Euler was actually the first guy to use the notation for a function, f of x. So whenever you see that f parentheses x, that was due to Euler. Euler was a very prolific mathematician. He wrote over 800 published papers in his lifetime, and his works would complete 90 volumes. In one of Euler's works, he looked at a constant that came up from numerous calculations, and it's since been known as Eulers Constant or Euler's number. Let's look a little more closely now at Euler's Constant. Euler's Constant, denoted by an E, is equal to 2.712818, etc. Euler's Constant is an infinite non-repeating decimal number, which we call a transcendental number in mathematics. You're already familiar with the transcendental number pi, 3.1415, etc. That's a number you've probably seen already in your studies. Euler's constant can be thought of as coming from a wide variety of areas, including things like geometry, the interest when you're talking about interest on a loan or interest you earn in a bank account, and other situations such as continued fractions. Euler's constant can be derived from a number of these situations, and you'll encounter these more later in your mathematical studies. Let's move on and talk about the function that results from Euler's constant, or the exponential function. Using that notation that Euler developed for functions, f of x equals e to the x is called the exponential function. This means we take that Euler constant number, 2.71, etc., and raise it to any number x as the power. For example, f of 1 would just be e raised to the 1 power, which is just e itself, or that 2.71, etc. The related function to the exponential function is the logarithm function. Here you see our logarithm function, g of x, equals log base e of x. We also denote this as ln. The ln stands for natural logarithm, or it's a special logarithm function where the base is e. The base is that little number written as a subscript of the logarithm. We read this as log base e of x. These two functions are very closely related to each other. Namely, they're inverse functions for each other. Inverse functions have the property that when we compose them together, they undo each other and we're just left with x. For example, a composition f of g of x or e to the ln of x just gives me x. Same thing if I compose them in the opposite order. G of f of x equals ln of e to the x power, and those exponentials and logs again undo each other and I'm just left with x. That's the inverse property of functions. You may have just seen we did this with a base of e. E isn't the only base you can use when dealing with the exponential and logarithm functions. Let's look now at the general exponential and logs. The general exponential function would just be f of x equals a to the x. A here is taking the place of some constant. A can be any positive number not equal to 1. So a has got to be greater than 0, but we won't let it be equal to 1. The reason is if a was 1, 1 to any power is just 1, and we'd get a constant function, which really doesn't satisfy the properties of exponential functions that we'll be talking about shortly. Another function we can look at, g of x equals log base a of x. Again, that subscript on the log stands for the base. We can convert back and forth between the logarithm and the exponential function according to if y equals log base a of x, this really just means that a to the y power equals x. Once again, these two functions have the inverse property. If I compose them together, f of g of x or g of f of x, the exponential and logarithm undo each other and I'm just left with the x. Let's do a quick example so you can see how the log works, because with different bases, sometimes this can be new to students. For example, what if I wanted to compute the log base 2 of 16? First, I'm going to notice to myself that 2 to the 4th power, or 2 times 2 times 2 times 2, is just equal to 16. So 2 raised to the 4th power is 16. In other words, log base 2 of 16 is asking the question, what power do I need to raise 2 to get 16? And the answer is 4, because 2 raised to the 4th power gives me 16. So you can see logarithm is kind of asking the inverse question of what power do I need to raise the base to get the quantity that I'm taking the logarithm of. Let's review some of the exponential properties that you'll see later in this course. You see a lot of properties listed here. You'll be talking about these in much more detail later on. But for right now, what you'll want to be noticing is that there's a lot of properties of exponential functions, and utilizing these will allow you to solve equations involving exponents. Specifically, exponential equations with e or any other base that we're talking about. A and b here are standing for bases. Remember, those numbers have to be positive and cannot equal 1. The logarithm also has a lot of properties. Don't worry about memorizing these now, but you will be utilizing them later to solve logarithm equations. Some of these properties come up again and again in calculus, so I highly recommend you pay attention now, learn these well, because that'll help you a lot later in your calculus studies. We can also consider the properties of the graphs of exponentials and logarithms. Here I've shown you an example of an exponential graph. This is if the value of a, or the base of the exponential, is greater than 1. If the value were between 0 and 1, the function would just be going down to the right and increasing on the left. That would be a base that's smaller, and it would be negative growth or decreasing function. Notice here, I've listed some properties of the exponential function graph. One of the key properties is all exponential functions go through the special point 0, 1. This is because anything raised to the 0th power just gives you a 1, and that's why that special point is on all of our exponential functions. Another property you'll notice from the graph is this function is continuous. There's no gaps, breaks, or jumps in our curve. This also has a horizontal asymptote at the x-axis, or y equals 0. Notice as I go to smaller values of x, the function gets closer and closer to the x-axis, but it actually never reaches it. That's why it's an asymptote. We also have the properties that this function increases as I go to the right and decreases as I go to the left. Finally, notice this function is 1 to 1. Remember, we check for functions being 1 to 1 by looking at the horizontal line test. Any horizontal line across my curve will intersect the graph at exactly 1 point and not more than 1 point. All right, let's now look at the exponential function's inverse, namely the logarithm function, for contrast. The logarithm function here is given by a graph like this. The logarithm function graph is also continuous because notice there's no breaks, gaps, or jumps. It goes through the special point 1, 0. It also has a vertical asymptote at x equals 0, or the y-axis. Notice that this function also increases as we go to the right, and as I head towards x equals 0, this function goes to negative infinity. This function is also one-to-one because notice any horizontal line through this function will intersect the graph at most one time. How are these two functions related to each other? Well, if you start to look at their graphs, you can probably see that these two functions are inverses, which we've been talking about a lot, and if we look at the graphs, you can see that more easily. So here I've graphed a sample of an exponential function with base e and a logarithm function, or natural logarithm, ln of x. The red line there is the line y equals x. Notice if I folded the screen over the red line, the two curves would line up on top of each other. That's because they're inverse functions, so they're basically a reflection across the line y equals x. Well, let's see, what are we going to learn about exponentials and logarithms in this course? In this unit, you will learn to, first of all, evaluate exponential and logarithm expressions. You'll also learn to convert back and forth between the exponential and logarithm form of an equation. You'll learn to graph those exponential and logarithm functions, particularly when you have transformations. You'll learn to solve exponential and logarithm equations. That's going to be one of the most important skills that you'll need to take with you to your calculus course. Finally, we'll talk about using exponentials and logarithms to solve application problems. Speaking of applications, what are the applications of exponentials and logarithms? There's quite a few applications, including population dynamics is probably the most standard one you'll hear about. If we look at the population, for example, the bunnies we looked at earlier, growing with time, you'll often see exponential growth. Radioactive decay is another popular application of exponentials and logarithms. You may have heard of carbon dating. Carbon dating is where they figure out the age of old artifacts using the decay of carbon over time. And that's looking at an example of decay. In this case, it's not radioactive, but we are looking at the decay of a substance. Also, if you're ever investing money in the bank, you're often getting compound interest. Compound interest is an example of an application of exponential functions. Newton's law of cooling is the law that tells you if you put a cake on the counter, how quickly that cake will reach room temperature, or if you put hot soda in the fridge, how quickly will that soda cool? That's Newton's law of cooling, and that is another application of exponentials and logarithms. Finally, the Richter scale for earthquakes. In California, you may be very familiar with this. The Richter scale for earthquakes is actually a logarithm function, and those numbers that tell you how severe an earthquake is actually based on a logarithmic scale. Sound intensity is another thing that is measured in logarithms. The sound intensity decibel levels is a logarithmic function. And finally, the learning curve, which is the rate at which you acquire knowledge, can be modeled closely by exponential and logarithm functions. So if you're looking to figure out how much information you retain as a function of time at which you're studying, that actually will be modeled by exponentials and logarithms. Well, I hope you enjoy learning about exponential and logarithm functions. Thank you, and I'll see you next time.